All right, so this lesson is going to pick back up where we left off in the middle of 2.2 notes. And what you've done so far is understand a normal distribution, single peaked, symmetrical, roughly symmetrical. The mean is in the middle of the peak. And then we talked about what percent of data is within each standard deviation from the mean. We talked about the 68, 95, 99, 7 rule, making sure that you understand that 99.7% of the data lies within 3 standard deviations. That is not 100% of my data, but it is the great bulk of the data is going to lie within 3 standard deviations. So we talked about being able to find the probability. I think we talked about an Iowa test score. Probability that a student score is between this number and this number. And as long as those were very nice numbers that landed exactly where a standard deviation was, then we can use the 68, 95, 99, 7 rule to kind of piece together the area under the curve for what we want and add that together to get the total probability for that particular question. What we're going to dive in today is what if it's not exactly 1 or 3 or 2 standard deviations above or below the mean. So we're going to introduce you to a function on your calculator. It's up there in purple. It's called normal CDF. So the normal is for the normal curve. CDF just means that we're finding the area under the curve in between two numbers. You're going to enter in the min and the max and the mean and the standard deviation for your data. And you're going to hit enter, and it's going to tell you exactly what the area under the curve is between that min and that max. So we're going to talk about a sunshine radio. The playing life of a sunshine radio is normally distributed, and that N should be capitalized, with a mu of 600 hours and a sigma of 100 hours. What is the probability that the radio selected at random will last from 600 to 700 hours? Okay, well, this is my normal distribution. I know that my mean is going to be right here in the middle. I know that I'm going to go 1 standard deviation, which is 100, so that's going to make that 700 and 800 and 900, and that's going to make this 500, 400, and 300. So I know that 99.7% of these radios will last between 300 and 900 hours. That's a very powerful sentence. I'm going to say that one more time. I know that 99.7% of sunshine radios will play between 300 and 900 hours. I know that 68% of sunshine radios will play between 500 and 700 hours. And while we're here, I know that 95% of the sunshine radios will play between 400 and 800 hours. So that's me applying that 68, 95, 99, 7 rule to an actual problem. Okay. Now, the question says, what's the probability that the radio selected at random will last from 600 to 700 hours? So I'm looking at this area. Well, guys, you know from the last video that that's 34%, because that's half of your 68%. So I can say that the probability that a radio selected at random will last from 600 to 700 hours is about 34%. What I want to use now is this. So I want you to write this down. We're going to normal CDF. All right, my lower number is my 600, and my upper number is my 700. So those are these two numbers right here that are cutting off the area. I know that my mean is 600, and I know that my standard deviation is 100. Okay, I'm going to grab my handy-dandy calculator, and we are going to use the button. Let's see, if you find the number 9 and go 3 buttons north of that. You should see a black button called VARs, stands for variables, and then the second function of that button says distribution, and that's where we're headed. So I'm going to go second distribution. We're going to live here on this button from now till May. So all of these in this list that you see, we are going to use. So right now we're at number 1 and number 2, and I do not want a normal PDF. I want a normal CDF. We will talk about the difference between those two, just not at this second. So I'm going to go down to number 2 and I'm going to hit enter. Now this calculator has the newer operating system, which I think is what most of you have. If you don't, if your screen does not look like this, if it pops up on the home screen and it just says normal CDF, then you're going to enter all of your numbers with commas in between them and then close your parentheses. If you have any issues with that, please ask and I'm happy to help you. Okay, so the lower, now this lower number that's currently in there looks rather odd. You should have run across E's on your calculator at some point, and you probably thought your calculator was doing an error. But technically, E on your calculator is scientific notation. So when this pops up on my calculator and I see -1 E99, technically what that means is -1 times 10 to the 99th power. Now that's a microscopically small negative number. It's technically it's a very, very big number, but it's negative, which makes it really, really small. So we're talking about a -1 with a 99 zeros behind it. So it is massively to the left. So that is the calculator's idea of negative infinity. Okay, so just when you see that, and we're going to be typing that in because we're going to need to go to negative infinity and positive infinity. So we're going to be using the 1E99. But right now, for this particular problem, my lower number is a 600. So I'm going to type in 600. My upper number is 700. There's my mu. Now notice your mu auto or defaults to a 0 and your sigma is a 1. So ladies and gentlemen, this is defaulting to a standardized test statistic. This is defaulting to your z-score, where your mu is always 0 and your standard deviation is always 1. So just FYI, that's why that's there. Okay, so I'm going to change this to 600 and my standard deviation is 100. I'm going to hit enter. So if you have the older version of the calculator, this is what you should be typing in: 600, 700, 600, 100. Gonna hit enter, and look at that. I get 34.134%. That is exact. Now notice our 68, 95, 99, 7 rule. It's a general rule. It's an approximation. So look how close it is. If we use that rule, we get 34%. If we use our calculator and go exact, we get 34.134%. So you're just going to need to make sure that you read the question very carefully. If I ask you to give me the probability using the rules and not using your calculator, then I would want the 34%. But if I ask you to be exact, then you're going to do the normal CDF. Okay, what is the likelihood that a sunshine radio will only last 450 hours? Well, guys, 450 hours is not on one of my standard deviations. It's 1.5 standard deviations below the mean. So that's where that 68, 95, 99, 7 rule is not going to be helpful at all. Okay, so if I want it to only last 450 hours, that means it is lasting all of these hours. Now, please make sure you understand, I'm not starting at 300. 300 is 3 standard deviations below the mean. That is not where my data stops. Technically, this can go to the left forever. So, when I type this in, I'm going to normal CDF. Now, you have two options. You can go all the way to negative infinity, or you can dabble a little common sense on this particular problem and know that the life of a radio can't be negative. So it could last for 0 hours. Like, we could get it and it could be broken, but it can't last for negative hours. So you can start it at 0. Either one of these is fine. Neither one is more right than the other. Okay, my upper limit is going to be 450 for both of them. My mean is still 600, and my standard deviation is 100. Okay, I'm going to go to my calculator. I'm going to go to distribution. I'm going to go down to number 2 and my lower limit. So I am going to type in 0. I'm headed to 450. Oh, not 4,500. And my mean and my standard deviation are the same. Now, I got 6.681%. One more time, because you have to be right to 3 decimal places. 6.681%. There's a 6.681% probability that a sunshine radio will only last up to 450 hours. Okay. And I knew that should be a small percentage because look at what we shaded in. That's really, really small. So that totally makes sense. What is the likelihood that a sunshine radio will last more than 825 hours? Okay, now hold on. 825 hours is going to be about here, and I'm going more than. So this should be tiny. This percentage should be really small. It should be smaller than the 6.681 because look at how much area you're shading. Okay, so I'm going to normal CDF. My lower limit is the 825. Now let's talk about what your upper limit is. Your upper limit is not 900. Remember, 900 is not the end all be all. It stops for 99.7%. So I have to allow for a sunshine radio that's going to last a really long time. Now, who am I to decide what that time is? Like, is 1,000 hours enough? Is 2,000 hours enough? So for here, I'm going to head all the way to positive infinity, and that's 1E99. My average is still 600, and my mean is still 100. So then I go to my calculator. I go to distribution. I go down to number 2. Let's see, I'm going from 825, all right, to infinity. Okay, so we have to practice typing this in, and that's that 1E99. So there's my 1. Okay, now your E is the button above the number 7, but it's the second function. So the button above the number 7 is the comma, but the second function of that, you'll see an EE, and that's what I want. So I'm going to do second, comma, and it gets me that E, 99. So that is, for your calculators, all purposes, that is positive infinity. If I wanted negative infinity, I would have done negative 1E99. My 600 and my 100 are staying put. I'm going to hit paste. Again, I'm looking for a small probability. And I got 1.222. So there is just over 1% probability that this Sunshine Radio is going to last longer than 825 hours. Okay. Sunshine Stereo cassette deck life is normally distributed with a mean of 2.3 years and a standard deviation of 0.4 years. What's the probability that a cassette deck will break down during the guarantee period of 2 years? So I hope you guys are starting to see who would actually use this information. If I've collected data on this cassette deck that's something that plays tapes that we are selling, and I'm going to offer a 2-year guarantee, I want to know how many of these I'm going to have to pay for. So if you can tell me the probability of how many are going to break down, then I can budget for that. Or maybe I need to lower my guarantee to only 1 year based on how long they're going to last. Okay, so I'm going to draw us a new curve. I've got a mean of 2.3 years. So X bar is 2.3, standard deviation is 0.4. I'm not going to go in here and do all the tick marks with all the standard deviations above and below the mean. I just want to give you a visual representation of what we're doing. So this is 2.3 years. So this is the life of the cassette deck player. I want the probability that the cassette deck will break down during the first 2 years. Well, if that's 2.3, then I'm just going to kind of estimate and say that's 2. And it's got to break down during the guarantee, so I know it's got to be less than 2 years. If it survives the 2 years, then I don't have to pay. I've got an average lifespan of 2.3 years, so it's looking good, but you know there's some variance there because I've got a standard deviation of a 0.4 year, almost half a year. Okay, so I need to find the area of that shaded region. So I'm going to normal CDF. Now, here's where you can either go to negative infinity, or you can use some common sense and know that the life of a cassette deck cannot be less than 0. Either one of these is totally fine. If you do negative infinity, they don't say, oh, well, they didn't have common sense and know that it wouldn't be a 0. Nobody's going to think that. Negative infinity, and I forgot my 1. Negative infinity is perfectly acceptable. I'm going to head to 2 years. I've got a mean of 2.3 and a standard deviation of a 0.4. Okay, so now I'm going to take my handy dandy calculator, clear that out. I'm going to go to distribution, down to number 2, and let's see, I'm going to do negative infinity. So negative 1 E 99, and I'm headed to 2 with a mean of 2.3 and a standard deviation of not 4, 0.4. There we go. Check it, make sure I'm good. Negative infinity, 2, 2.3, and a 0.4. So I'm going to go to paste, hit enter, and I get 22.663%. 22.663%. Okay, so if I'm the statistician for, I don't know, Fisher Price, and we're making this cassette deck that's going to go out the kids can play with, I'm going to go tell the CEO, or I'm going to go tell the finance department, listen, we've gathered data. The mean of these things are about 2.3 years. If we do a guarantee of 2 years, we're going to be replacing 22% of these things. So then financially, now my business majors, my accountants, are going to swoop in and decide if that's financially responsible. If it's not, if it's going to cost us too much money, then I'm either going to raise the price of my cassette decks and make more money off of the ones I don't have to reimburse, or I'm going to lower my guarantee period to maybe a year. Okay. What if we converted the Sunshine Radio problem to z-scores and used a standard normal distribution? Would you get the same answer? Okay, well, you know, if you're a standard normal distribution and we are talking z-scores, then ladies and gentlemen, your mean is always 0 and your standard deviation is always 1. Always, always, always. Okay, z-scores. The z-score tells you how many standard deviations above or below the mean your data is. Okay, so now it says, what is the likelihood that a Sunshine Radio will only last 450 hours? Well, if I look back to where we've already done that one, I got 6.681%. So what I want to show you is that if you can use z-scores, you will get the same answer. Now, normally as mathematicians, like, we don't really care that there are two ways to do something. You show me a way and it will work all the time, then that's the way I'm going to do it. But in statistics, sometimes it is more beneficial to use a z-score instead of the raw data. So this is something that's really, really important, and they can build multiple choice questions that force you to go the z-score route. And the multiple choice questions would be like, what would be the setup for finding the likelihood that a Sunshine Radio will only last 450 hours using a standard normal distribution? Okay, so standard normal z-score. So first I'm going to find his z-score. So on that formula sheet, I know that it's x minus x bar over the standard deviation. My piece of data is 450 hours. My mu is 600 hours, and my standard deviation is 100 hours. So now I'm going to take my calculator, I'm going to find my z-score. So I'm going to do 450 minus 600, hit enter, and then I'm going to divide it by my standard deviation, which is 100. And I got a z-score of a negative 1.5. Now, does it make sense? Like, let's think about this and let's make sure it makes sense. Does it make sense that my z-score is negative? Yes, it does, because 450 is below the mean of 600. Does it make sense that my z-score is a negative 1.5? Well, yes, it does, because that would put it about here. And if my standard deviation is 100, that would be 150 hours less than the 600. Remember, if you get a z-score that's anything above a 4 or a negative 4, really that's above a 3 or a negative 3, something's off. Remember, 99.7% of your data lives within 3 standard deviations of your mean. So if you're doing a problem and you get a z-score of a negative 12, something's wrong. So don't forget to sprinkle that common sense kind of last resort to double check your answer. Okay, so I need to find the normal CDF. Now remember, we're talking about standard normal distributions here. So I'm going, will only last, okay, so less than that. I'm going from negative infinity to my z-score of a negative 1.5, because that's what this is right here, with a mean of 0 and a standard deviation of 1. Again, my mean is not 600. My standard deviation is not 100. We are now standardized. So we are now completely talking in terms of how many standard deviations above or below the mean you are. So I'm going to grab my handy dandy calculator, and I'm going to distribution, and I want number 2, and I'm going to keep my negative infinity there. And I'm headed to a negative 1.5 with a 0 and a 1. And I think what we're looking for is 6.681. Let's see how close it gets. 6.681. Dead on it. Dead on it to 3 decimal places at least. So I hope that you guys can see that we just answered the same exact question from the top of the page down here, but we did it here with z-scores. Likelihood that a sunshine radio will last more than 825 hours. All right, I'm going to find a z-score for 825 hours. The more you practice the z-score, the better you get. So 825 minus the 600 over 100. I can already tell this is going to be positive, which makes perfect sense because we are above the mean. So 825 minus 600 divided by 100, 2.25. So now I'm going to normal CDF. Now this 2.25, so likelihood that a sunshine radio will last more than 825 hours. So I'm 825 and up. So I'm 2.25 and up, and I'm going all the way to infinity. I'm not trying to estimate how high this thing will get, how many standard deviations. I'm definitely not going to put a 3 there because I know that's not all of my data. It's only 99.7%. I don't really want to just go to 4 because what if there's that 1,000-pound alligator out there or the 20-pound New York City rat? So I'm just going to go all the way to infinity. And because I'm talking about z-scores, my mean is always going to be 0 and my standard deviation will always be 1. If I look back to the top of the paper when we found it using the regular data, I got 1.223. So let's type this in and see if we get the same. So normal distribution, and let's see, 2.25 to infinity with a 0 and a 1. 1.222. All right, so just slightly off, but made it to the 10th, 100th, 1000th decimal place. So 1.222. So extremely close. Extremely close. Okay. Okay, so now we're going to pick the pace up just a little bit, and we're just going to practice kind of typing this stuff in. Okay, I've got Z, so everybody should know what Z is. Z is a standard normal distribution, so this is a Z-score. Be a random variable with a standard normal distribution. Find the area between a Z of 1 and a Z of 2.7, and I've got a curve here. Now let me make sure this is really, really clear of what the expectations are on a test. If you have an FRQ and you are finding the area under the curve, you are expected to draw the curve and to label what you're finding. So if on this test you're going to have to find the area under the curve, part of your points will come from your graph and your labeling and your shading. So if this is a z-score, I know that's 0. 1's going to be here. There's going to be 2. There's 3. So 2.7 is in here. So I'm going from a 1 to a 2.7. So I'm all of this. That's all I need. You don't have to label everything. I just need a visual graphical representation of what we're finding. Okay, so if I want the area in between, I'm going to go normal CDF from 1 to a 2.7. Now this is a standard normal distribution, so we are talking z-scores, so your mean will always be 0. Standard deviation will always be 1. I'm going to grab my calculator, go to distribution, down to number 2, and I am going from a 1 to a 2.7 with a 0 and a 1, and I got 15.519. 15.519%. Or if you don't want to scoot your decimal, you can just give me 1.55, but then obviously don't make it a percent. I'm good with either one of these. You need to be able to be flexible. If it's multiple choice and they went percent, be able to go percent. If they don't go percents, they're leaving it as a proportion. So then you can go decimal, but just make sure you go 3 decimal places. Either answer is equally fine. Okay, the next one says find the area to the right of a 0.94. So I'm going to go in here and call him a 0.94, and I want everything to the right. So I want all of this all the way out. So I am a normal CDF. I'm going from a 0.94 and I'm going all the way out. And who am I to say where it stops? I'm going to infinity. I'm a standard normal distribution, so it's going to be a 0 and a 1. Grab my calculator, going distribution. Number 2, I'm going 0.94 to infinity with a 0 and a 1. And I got 0.174. If you don't turn it into a percent, or I'm getting 17.361%. Either one is fine, but again, you have to be correct to 3 decimal places. Okay, so these next 3 are all z-scores. I know that because I see the z's. Also, all my numbers look to be very small, nice in between a 3 and a -3. So I know these are z-scores. Okay, so I want you to pause it. I want you to use the graph provided. I want you to draw and shade and write out normal CDF and what you're typing in, and then get your answer. Remember, if you type it in your calculator, you need to write it on your paper. So you cannot normal CDF all this stuff on your calculator, but not explain to the grader what you're typing in. So make sure you show that step, and it will cost you points on my test if you don't show that step. Okay, so pause this and knock these 3 out and then hit play and check them. All right, so 0, 1, 2, 3. I'm going from a 1.15, so that's going to be about there. Shade all of that. This is the part I was talking about making sure you write what you're typing in. I got a 0.125. Let's see, if I am 0.25, 0.25 is right there, and I want less than. So that would be all of that shaded. Now I can already tell this is going to be over 50% because I know left of 0 is 50%, and I'm a little bit more than that. So see how I'm using my logic to kind of make sure my answer's in the right ballpark. So for this one, I'm going to normal CDF from negative infinity to a 0.25 with a 0 and a 1, and I got 0.599, which would be 59.9%, which is bigger than 50%. And then the last one, I'm going from a negative 1.78, so that's going to be about there, to a 0.35, which, I don't know, going to be about there, and I want all of that. So I'm going to normal CDF from a negative 1.78 to a 0.35 with a 0 and a 1. No infinity here because it's bounded on both sides. Normal CDF, negative 1.78, 0.35, 0, 1, 59.929%, or 0.599, either one. Okay, So I hope everybody's comfortable with the graph, whether it be a standard normal graph or a plain normal graph. The difference between a z-score or doing a normal CDF with a z-score and doing it with raw data, like we did at the beginning with the Sunshine Radio. So again, this is building upon what you learned in 2.1 and the beginning of 2.2. So if you're iffy, pause it, go back, find the resources to help fill in the holes. Okay? All right. So this says let x have a normal distribution with mu to be 10 and sigma to be a 2. Find the probability that an x value selected at random from this distribution is between 11 and 14. And I want you to show it in two different ways. One with a normal distribution and one with a standard normal distribution. Okay. So I'm going to cut this in half. This one's going to be for the normal distribution and this one's going to be for the standard normal distribution. For the normal distribution, I know that my mu is 10, my sigma is 2, and what I'm looking for is in between 11 and a 14. So I'm going to draw my curve because I cannot normal CDF without a picture. Average is at 10, and I'm going from an 11 to a 14. Now, guys, I don't know how far away that is. Again, it's just a visual representation. I know it's to the right, but I don't know how far. I'm not taking my time to put tick marks on here. I'm going to normal CDF from 11 to 14. Now, this is not going to be 0, 1 because this is not a standard normal distribution. This is just the normal distribution. So 11 to 14, and then my mean of 10, and my standard deviation of a 2. I'm going to type that in just a second. All right, now for a standard normal curve, I need a z-score. So I need to take this 11 and this 14, and I need z-scores for both of them. So I'm going to do 11 minus the mean over 2, and I'm going to do 14 minus the mean over the standard deviation. Well, 11 minus 10 is 1, and 1 over 2 is a 0.5. And 14 minus 10 is 4, and 4 divided by 2 is 2. So I have a z-score of a 0.5. I know that my distribution is going to be centered around 0, so I'm going from 0.5 to 2. Again, I'm not putting tons of time into that, but you do need a visual, a graphical representation of what you're doing. So then I'm going to normal CDF 0.5 to a 2. But remember, this is standard now, so my average is a 0, and my standard deviation is a 1. Now I'm going to grab my calculator, and I'm going to type both things in, and I should get the same answer. So distribution number 2, we're going from 11 to a 14, standard deviation of a 10, nope, mean of a 10, standard deviation of a 2. And I'm going to get 0.286 or 28.579%. Again, I'm going slowly to make sure you're good with your rounding, because let me tell you how bad it would suck to get all this work right, but miss it because you don't know how to round. You have to be 100% accurate to 3 decimal places. Okay? And so now I'm going to do the other one. And I am going from a 0.5, oh, I got 2 decimals up there, 0.5 to a 2, and I'm standardized, so now my mean and my standard deviation is a 1. I hope that this is starting to come together and make sense, going back and forth between a normal and a standard normal. So you guys can see that it is right to 3, 6, 9, 12 decimal places. It is correct. Yeah, 10 decimal places. So 0.286 is the probability, or 28 point whatever the decimals were. Okay, so guys, that's it for normal distribution. So we're changing gears. So if you need to pause the video and take a break, feel free. But we're changing gears. Here we go. So now, what we've done up to this point is, I have given you the two values, or one value, and you've been able to go to that graph, the curve, shade in what you're trying to find, and normal CDF it to find the area under the curve. Well, guys, now we're going to go backwards. I'm going to tell you the area I want, and you're going to tell me what numbers will get me that area. Okay, so if you think about it, it sounds like we're going backwards. We're doing the inverse. So that's why we're using inverse normal distribution. So it says, what if we need to find our z or our x values that correspond to a given area under the normal curve? Okay, now you've got inverse norms. That's inverse normal distribution. Inverse norm. You're going to use inverse norm when you are given area. Okay, inverse norm only works with percent to the left. And we'll explain what that means. And then you need the mean and you need the standard deviation. Okay, now just sidebar for just a second. Let's talk about percent to the left. What if I say, how many hours will a sunshine radio last if I want, no, that's not going to work. It's hard to think of these on the fly. Okay, so let me try to not come up with a word problem. If you had a word problem that said I needed 20% area to the right, or 0.2 area to the right. Okay, well remember, this only does percent to the left. So I would not put 0.20 right there. I would put 0.80, because if it's 20% this way, then I know it's 80% that way. So inverse norm only inputs area to the left. So if you are given area to the right, you have to convert it to area to the left, knowing that the total area under the curve is 100%. Okay, here we go. Magic Video Games Incorporated sells an expensive video computer games package. Because the package is so expensive, the company wants to advertise an impressive guarantee for the life expectancy of its computer control system. The guarantee policy will refund full purchase price if the computer fails during the guarantee period. The research department has done tests which show that the mean life for the computer is 30 months. That doesn't seem long at all, with a standard deviation of 4 months. The computer life is normally, that should be capital N, normally distributed. How long can the guarantee period be if management does not want to refund the purchase price on more than 7%? So management, accounting says, all right, we can handle refunding 7% of what we sell, but I can't do any more than that. So how long do we need to set our guarantee period at? Okay, when you get a problem like this, start with a curve. You know that you have a mean of 30 months. I am not going to refund. Think about on this curve, if this is the life of this computer, where you're going to refund people. I'm going to refund people if it breaks too soon. If it lasts 40 months, I'm not refunding your money. You just went above average. I'm going to refund down here somewhere. So the problem is, I'm not telling you where. I'm asking for where. But I am telling you that I can't go more than 7%. That is your area. So guys, this right here, this is a question mark. This area right here is 7%. So I have the area. I need to know what value will cut off that much area. So I'm going to use inverse norm. Now remember, inverse norm does percent to the left. Well, I have percent to the left. It's 7%. So 0.07 with a mean of 30 and a standard deviation of 4. Now when I type this in, and I'll show you where inverse norm is, it's going to give me that question mark. It's going to give me the value where I should chop this off. So I'm going to my calculator. I'm going back to distribution, and then look at number 3, inverse norm. So inverse norm, I take my area, which is 0.07. My mean was 30, and my standard deviation was 4. And I'm going to paste. And I got 24.0968. So 24.0. All right, let me tell you about my feelings about 0 as your first decimal. When they say they want 3 decimal places, 100% I'm on board with that. But I don't like 0 as a first decimal place. I want 3 decimal places with a meat on it. So I'm not going to count the 0. So in this case, I'm going 4 decimal places. Technically, you don't have to. They said 3 decimal places. So if you went 24.097, you're 100% correct. For the life of this class, I'm going to go 3 decimal places, and I don't like 0 as a starter. So I'm going to write 24.0968. Now, please don't put a percent sign on this. This is not area. This is that number right there. This is months. The question said, how long can the guarantee period be? Well, it can be about 2 years. 24.0968 months should only cause us to refund 7% of our purchasers. Okay, so what I have circled is your answer. Okay, now watch what I'm going to do. Let's go backwards. What if I normal CDF from negative infinity or 0, because you can't have negative time, to 24.0968 with a mean of 30 and a standard deviation of a 4. Now, when I type this in, think about what I should get. This finds the area, and the area is 7%. So let's test it. I'm going to normal CDF. And let's see, that was, I'm just going to go from 0 to 24.0968 with a mean of 30 and a standard deviation of 4. 7%. 6.9998, and that 8 would round the 9 up, and then 9 would round the 9 up, and then 9 would round the 9 up, and that 9 would round the 6 up to a 7. So it is 7%. Now please make sure you understand, guys, what I just did, this normal CDF, that's not part of the problem. That's me showing you the relationship between an inverse norm and a normal CDF. So here we go. To be clear, a normal CDF finds the area under the curve. The inverse norm finds the place that will cut off a given area. Inverse norm is when I have the area, I just need to know where to slice it. Normal CDF says, I know where I'm slicing it, I want to know how big the slice is. What is the area of the slice? Okay, find the z-value so that 90% of the area under the standard normal curve, okay, standard, we're z-scores now, lies between negative z and z. Find the z-value so that 90% of the area. Okay, I am given area. I see it. It's right here. They gave me area. I'm going to draw. 90% of the area between negative z and z. Now, these are the same numbers, so we're talking symmetrical. So I want, and 90 is going to be a lot. So I want him and him so that I get 90% of the area is in between those two z's. Now, remember, this is symmetrical, and a standard normal curve is centered around 0. So guys, when you find one of these z's, you know the other one. Like if I get a 2.7, then I know the other one's a negative 2.7. It's symmetrical, okay? Now, focus with me on the fact that this is 90%. Remember, we need to think percent to the left. So I need to know how much this is. I don't care about this. I don't care about this. I want this. And that's going to find me this guy right here. Well, if that's 90%, then I know there's 10% left because the whole thing is 100%. So I'm taking out 90. It's going to leave me with 10. But I know that that 10% is split between the two wings. So then I know each wing is 5%. All right, I'm going to say that one more time. 90% in between the z and the negative z. So I know there's 10% unaccounted for. There's 10% left, and again, I know I'm symmetrical. If there's 10% left, then I know there's 5% in each of the wings. So I know there's 5% here and 5% here. This is the one I'm interested in because I want area to the left. Now again, I was given area, so this is inverse norm. 5%. This is a standard normal curve, so I'm 0 and 1. I'm going to take my calculator. I'm going to inverse norm. My area was 0.05 with a 0 and a 1. And I got negative 2.576. Make sure you're rounding correctly. Negative 2.576. So this z-score is a negative 2.576, and it's symmetrical, so I know this is a positive 2.576. So you may see in my answers a plus or minus, and that's just a very quick way to write both numbers. Okay, find the z-value so that 3% of the area under the standard normal curve lies to the right. Okay, there's my curve. 3%, gonna be way over here. That is 3%. I want that z-value. Well, what is the area to the left? Well, if that's 3%, area that's left is going to be 97%. So I'm going to inverse norm 0.97 with a 0 and a 1. Go into my calculator. Nope, that's not what I want. Inverse norm 0.97, 1.881. Now, notice I did not write just 1.881. I wrote z equals. This is a z-score because I'm talking about a standard normal curve. So this is the z-score. Suppose the time to complete a test is normally distributed with a mean of 40 minutes and a sigma of 5 minutes. After how many minutes can we expect all but about 3% of the test to be completed? Okay, when you see that 3%, you know that you have been given area under the curve. So I know I'm going to use an inverse norm. I'm going to draw my curve to represent the information that I was given. I have a mean of 40 minutes. I want everybody finished but 3%. And remember, this is minutes. So all these people are finishing, and I want to know how many minutes it takes to have all but 3% be finished. This is finished. This is not finished. So I want to inverse norm 0.97 40, comma 5. This is not standard normal. I'm not using a 0 and a 1. Go to my calculator. Inverse norm, 97% stays put, 45. 49.404. 49.404. Okay, is that a z-score? No, don't set it equal to z. That's 49.404 minutes. I can tell, or I can guess, that about 3% will be left to be completed after 49.404 minutes. If I normal CDF from 49.404 to infinity with a mean of 40 and a standard deviation of 5, I know I should get about 3%. Remember, you're doing the opposite. You are given the percent. I'm asking where should you slice it to get that percent. That's why it's called inverse norm. Okay, one day on the driving range, Tiger Woods practices his swing with a particular club by hitting many, many balls. Suppose that when Tiger hits his driver, the distance the ball travels follows a normal distribution with a mean of 304 yards and a standard deviation of 8 yards. What percent of Tiger's drives travel at least 290 yards? All right, so I'm throwing you a curveball. Is this normal CDF or is this inverse norm? Remember, normal CDFs finds the area under the curve. Inverse norm, you're given the area and you're asked where to slice it to get that area. Okay, do y'all see the question? It says, what percent? When you see what percent, it's asking you for the area. So when it says what percent, I know I am no, when you see what percent, I know that I am normal CDF. I'm a normal CDF because it's asking me to find the area. So I'm going to normal CDF. Travel at least 290 yards. Oh, let me graph. Let's see, his average is 304. And we're going 290, so that's going to be less than that. And I want at least 290, so I want this. So I know it should be more than 50%. Now, again, I graphed that really fast, so make sure that makes sense. I threw the average on there. I know where 290 is in relation to 304. It says at least 290, so I know I'm shading above it. So I'm going to go from 290 definitely to infinity because I have no idea how far he can hit this golf ball with a mean of 304 and a standard deviation of 8 yards. So I'm going to distribution and I'm going to normal CDF. I'm going from a 290 to infinity with a mean of 304. No, 304, there we go, and a standard deviation of 8. And I know it should be more than 50%. Oh, wow. 95.994%. Okay. What was it? 95.994%. And again, that's area under the curve, so that gets a percent symbol. You could have left it as a proportion and put 0.95 0.99 if you wanted to go 4 decimal places, but if you wanted to go 3 decimal places, that would be a 0.960. What percent? There it is again. I know I'm a normal CDF. Between a 305 and a 325. All right, now 305 is going to be here. 325, I don't know, somewhere over there. I know I'm going to be less than 50% now. I'm going from 305 to 325 with a mean of 304 and a standard deviation of 8. Let me go type that sucker in. 305, 325, nope, yep, 325, 304 and an 8. 44.593%. 44.593% of his drives should travel between 305 and 325 yards. Okay, home stretch, hang in there. High levels of cholesterol in the blood increase the risk of heart disease. For 14-year-old boys, the distribution of blood cholesterol is approximately normal, with a mean of 170 and a standard deviation of 30. What is the first quartile of the distribution of blood cholesterol? Mean of 170. First quartile. Well, I know that's 50%. So I want 25%. First quartile. Well, looky there. I want 25%. They gave me what percent I wanted. I want to know the value that will chop off 25%. That's inverse norm. Percent to the left, 25%. Mean, 170. Standard deviation, 30. Inverse norm, 25%. 170. Oh, not a plus sign. 3. Oh, hold on. I typed in a 3 and not a 30. Let me try that again. Number 3. There it is. 30. There we go. 149.765. This is not a percent. The percent was 25%. I just found the cholesterol level that will chop off the first quartile. So I don't know how this is measured. So I'm just going to put cholesterol. There's an H. Hold on. Level. I chopped off my 1. So 149.765 is the cholesterol level for 14-year-old boys that will chop off the first 25% or the first quartile. Okay, last problem, and it's the big one. So again, if you need to take a break, pause it, take a break, come back to it. This is the Mac Daddy of application problems. An important measure of the performance of a locomotive is its adhesion, the pulling force, as a multiple of its weight. The adhesion of one 4,400 horsepower diesel locomotive varies in actual use according to a normal distribution with a mean of 0.37 and a standard deviation of 0.04. The locomotive manufacturer is considering 2 changes that could reduce the percent of times the train arrives late. One option is to increase the mean adhesive of the locomotive, and the other possibility is to decrease the variability in adhesion from trip to trip, that is, to decrease the standard deviation. Okay, let's pause here for just a second. So we have a train, and we're talking about its adhesion, which is the pulling force. Now, trains run on a schedule. I need the train to arrive when it's supposed to arrive, not early and not late, because I got other trains coming to this station. I got people waiting. They're trying to connect to another train. I need it to run like clockwork. So the arrival time percentage on time and its standard deviation is very important to this. Okay, so the first thing I want to point out, and I'm just going to go in this blank space, and you can just go over to the side, is that, okay, it says that it follows a normal curve. It has a mean of 0.37 with a standard deviation of 0.04. Now, this is its adhesion time. So, or its force. So as the adhesion force gets lower down here, then it's not pulling as hard, which means it's going to be slower, which means we are going to be late. If the adhesion force gets stronger, then it's going to be pulling the locomotive faster, and that means we are going to be early. I don't want to be either. I want to be on time. But I just wanted to make sure you understood the train part of this. Okay, so if I look at part A, it says, if the standard deviation remains at a 0.04, to what value must the manufacturer change the mean adhesion of the locomotive to reduce the proportion of late arrivals to only 2%? Okay, they just gave you a percent. So they just gave you area under the curve. So you should already, like the brain should already be clicking all this stuff going, that's a percent, that's area under the curve, I'm going to inverse norm something. Okay? But before you do that, we've got to figure out where this 2% is. Is this 2% on the left or is this 2% on the right? Okay, well, it's talking about late arrivals. Okay, and you know that its late arrivals are going to be down here. So I want what number this needs to be so that that is 2%. So I want to inverse norm 0.02, and then I want my mean and my standard deviation. Okay, but let's read the question one more time. If the standard deviation remains at 0.04, okay, to what value must the manufacturer change the mean adhesion of the locomotive to reduce the proportion of late arrivals to only 2%? So guys, I'm looking for the mean. I'm looking for the mean. So I don't have a mean to put in here. It's saying I'm going to change this. So I can't use the 0.37 if the standard deviation remains at 0.04. So that's locked in. To what value must the manufacturer change the mean adhesion of the locomotive to reduce its proportion of late arrivals to only 2%? So guys, if I had done this, then this would be off because I don't want my mean to be 37. It's asking for me to change the mean. So what I'm going to do, because I can't inverse norm unless I have a mean, is I'm going to standardize this. So I'm going to inverse norm 0.02 with a 0 and a 1 because that's universal. So I have now switched from a mean of a 0.37 or whatever I'm trying to get it to be to a mean of 0 and a standard deviation of 1. So I have switched from regular data to z-scores. Okay, I'm going to inverse norm 0.02, 0, 1. I know that's going to be really, really small. You type that in and you are going to get, and I'm going to label it with a z, you're going to get a negative 2.0537. Now, number one, understand that this is a z. Number two, know that why this is a -2 and some change. That's a tiny, tiny small amount of area, and it's way, way left. So I know I'm going to be negative, and I know that my z number is going to be really, really, really close to -3 because there's a very little area under the curve out there. Notice also I went 4 decimal places because I don't like 0 as a starting decimal place. So I now have the z-score. Okay. Now, we haven't even made the big leap yet. Here's the thing. You have a z-score. You have a standard deviation. You also have, hold on one second. So think about a formula that relates a z-score to a mean and a standard deviation. Okay, so I skipped over this guy. Let's read him. It says the locomotive needs to have an adhesion of at least a 0.3 for the train to arrive on time. If it's less than a 0.3, the train will be late. An adhesion greater than a 0.5 will result in the train arriving too early. So I need to be between a 0.3 and a 0.5. Okay? So if I know that the piece of data, the train, needs to be in between a 0.3 and a 0.5 to be on time, to be considered on time. And I'm talking about it arriving late, and that's on this side. Then I need to not go below that 0.3. So the formula that relates z-score and mean and standard deviation is the formula for z-score. Remember? This is on your formula sheet, but it's in words. Now, I know my z-score. I just found him. I know my standard deviation because they told me that wasn't going to change. I am looking for my mean. That's what they have asked me for. So the kicker is, where does your x come from? Well, guys, your x is the value that you can't go below in order to be on time. So that's as low as I can go. So we're going to let that be the x. So now I'm going to plug all this in. Nope, I know what x is. So this z-score formula, remember, you can use formulas when you have some pieces and not others. So I can use this formula, obviously, when I'm trying to find a z-score, but I can also use it to find a sigma or a mu when I'm given the other 3 pieces of data. So now I'm going to solve this. And what I have found in years past, students really struggle with solving this equation that I've written in blue. So your first step is going to be to multiply both sides by 0.04. And then you're going to subtract the 0.3, and then you're going to divide by -1. Okay? So I'm going to take the -2.0537. I'm going to times it by, I'm timesing both sides by the 0.04. And then I'm going to subtract 0.3 to move that over. That's going to equal negative mu, so then I know my mu is a positive, if I divide by -1, 0.382. Okay, that was a big one. Okay, last one, or B and C. C is a conclusion. If the mean stays at 0.37, how much must the standard deviation be decreased to ensure that the train will arrive late only 2% of the time? Okay, so I'm still talking about arriving late. So I'm still at that 2% to the left. So I have the same z-score. I don't have to find that again. So my z-score was a negative 2.0537. Okay. I'm going to use my z-score formula. I know what z is, so I'm going to plug that in. To not be late, I know that I needed to be a 0.3. I'm keeping my mean at a 0.37, but I want sigma. Okay. To solve this equation, first I'm going to subtract the two things that are on top. Now I'm going to multiply both sides by sigma. And then I'm going to solve for sigma, I'm going to divide both sides by negative 2.0537. So I'm typing in negative 0.07 divided by negative 2.0537. And I get a sigma of a 0.0341. Part C says, which of the two options do you think is preferable? Well, think about what would happen. We focused on the fact that we don't want to be late. But think about these adjustments and what it would do overall. If I up my standard deviation, no, if I up my mu from a 0.37, which is what it is now, to a 0.382, my mu, my average, then yet it'll fix the arriving early too often or arriving late too often. But if I up my standard deviation, that makes the train faster overall. Because remember, that's what you're measuring. You're measuring the adhesion. If I make it faster, then it'll help me not be late, but it will make me arrive early more often because it shifts everything up. If I change my standard deviation, I'm changing the variability. So my measure of center stays put at 0.37, but the data kind of gets sucked in and becomes less variable. So not only will it reduce the amount of percent of time that I am early or that I'm late, it will also reduce the amount of time that I am early. So of the two options, I'm going to change my standard deviation. But you need to be okay with the explanation there. So feel free to pause it, rewind it, and listen to that again. While experience can suggest whether or not a normal distribution is a reasonable model in particular cases, it is risky to assume that a distribution is normal without actually inspecting the data. The data should be roughly symmetrical, doesn't have to be perfect, but definitely can't be right or left skewed. It has to be unimodal, it has to be bell-shaped. The max and the min should be about 3 standard deviations away from the mean. Remember, that's 99.7% of your data. So if you go beyond that, if your max is 5 standard deviations above your mean, that's not unheard of, but odds are something's off and it's not normal. So if I ask you if a normal distribution would fit this data, these are the things you need to be looking for. The data should be roughly symmetrical, unimodal, bell-shaped, and the max and the min should be about 3 standard deviations away from the mean. Okay, that was a ton of information. I want to make sure that you know the difference between that and that. You use this when you want area under the curve. You use this when you're given area under curve. and then make sure that you're super comfortable going from a regular piece of data to converting it to a z-score, and make sure that you are best friends with him.